Hello students, we discuss today motional EMF, which is part of electromagnetic induction. So today we see that how EMF will be created when a conductor is moving inside the magnetic field. For example, I am taking one magnetic field which is into the board. Okay, so it's a constant magnetic field and direction of the magnetic field is into the board. Now randomly I am taking the one conductor which is a straight conductor, and I am taking that the conductor length is dl, means very small part of the conductor I am taking. dl is the length of the conductor I am taking, which is very small part of the conductor I am taking. I am supposing that if conductor is moving with velocity v. See, this is the one case I am taking, but it is not a, what do you say that, completely describing the concept. It is a simple one case, and we write down the general expression so that anywhere we can apply the formula. Okay, so as the rod is moving with velocity v, then in the magnetic field, now I am taking like this. This is the rod, okay, moving with velocity v, magnetic field is into the board. Now the free electron inside the conductor, as the rod travels, free electron inside the conductor also will travel with same speed v. So at a particular instant we are talking about. This is completely instantaneous. So rod is having the instantaneous velocity v. Then magnetic field is b at that instant or at that rod place. Then the free electron inside the rod will also travel with v speed in forward direction. Then we know that any charged particle is moving inside the magnetic field, that will experience a force because of magnetic field. So that force value we can write down. The force is equal to, force due to magnetic field is equal to charge into v bar cross v bar. This is actually force value, force direction as well as magnitude. Now I will apply for the electron thing. Force magnitude I am writing. Force due to magnetic field I am writing as Fm is the charged particle magnitude is E. Now V bar cross B bar. V bar is on the board towards right, whereas B bar is into the board. The angle between V bar and B bar is 90. V bar inside, B bar is there. So it will be at an angle 90 like this. V bar and B bar inside. So then I can write down VB sine 90 is the magnitude. So ultimately force due to magnetic field is equal to E into V into B. This is the force due to magnetic field. Now if this is the force magnitude, then what is the direction? The direction of the magnetic force due to magnetic field is in the direction of V bar cross B bar if charge is positive. If charge is positive, V bar cross B bar direction and F bar direction will be same. If charge is negative, V bar and B bar direction will be opposite to F bar. Now this is V bar and B bar is inside, then V bar cross B bar will give you upward, something like this. This is V bar, this is the B bar is inside, I wrote like this. V bar cross B bar direction will be upward, this is the V bar cross B bar direction. But we require the force acting on electron which is a negative charge. As it is a negative charge, the direction of force on electron will be opposite to V bar cross B bar. So the direction of the force will be downward. Because V bar cross B bar I am getting upward, then force acting on electron will be downward. Then this is the force due to magnetic field on the electron. So because of this force, the electrons will start moving downward. Then electrons will accumulate here. Then it will accumulate some negative charge. So negative charge will be accumulated on the bottom side. So it results in the positive charge accumulation on the top. This is the positive charge. Positive charge accumulation. So at the bottom negative charge will accumulate. At the top positive charge will accumulate. Then positive to negative, there exists a field, electric field. That is E bar downward. So now first electron will come. Then minus E plus E will be the charge. Second electron will come. Plus 2E, minus 2E I am here, plus 2E will be here. So once first electron came here, second electron will experience repulsion by the first electron. but that repulsion will be less compared to this force. Like that third electron, as the third electron is coming downward, that will experience a repulsion by 2 electrons already settled at the bottom. So like that every electron which is coming downward, that electron will experience a repulsive force. So that repulsive forces we are writing as in terms of electric field. Now I am supposing that some n electrons came here. So minus Ne will be the charge at the bottom, plus Ne will be the accumulated at the top. Then plus Ne to minus Ne, there exists an electric field. This electric field will apply force on n plus 1 electron. So n plus 1 electrons, all electrons will experience the force downward because of the magnetic field. That is same. All n electrons and even n plus 1 electron also will experience the same force downward by magnetic field. But all these n plus 1 electrons won't experience the same force by the electric field, because as the charge is accumulating, the electric field value will change, the force value also changes. So then it results in some force upward that I can write down E into E, because charge is negative, opposite to field force will act. This is the force due to electric field. I am supposing that n plus 1 electron, on n plus 1 electron, these two forces are equal. Force due to magnetic field and force due to electric field are equal. If that is the case, force due to electric field and force due to magnetic field is equal, then n plus 1 electron won't accumulate, or n plus 1 electron won't come downward. That means plus minus Ne and plus Ne will be the charge, will stay in equilibrium, or you can say stay in stable condition. Okay, so that's why I can write down the field due to, force due to electric field is equal to E into E is equal to force due to magnetic field, which is E into V into B. Then E cancels out, then electric field value is equal to V into B. This is the electric field value. But I want to know that what is the potential difference between these two ends. So this is the rod, given rod, and this is the electric field. As I am taking a very small part of the length, this electric field is uniform. Okay, usually plus here plus Ne will be there according to my example, minus Ne, I don't know what is the n value. N value you cannot define now. Okay, so positive charge and negative charge accumulated at the ends, it will act as something like a capacitor plate. This is one plate of capacitor, this is other plate of capacitor. There exists an electric field. Okay, so then I want to know potential difference value. Usually potential difference we can write down dV is equal to minus E bar dot dl bar. This is the potential difference, means along the field potential decreases, means this will be higher potential VH I am writing, this will be at lower potential VL, then I am writing directly VH minus VL. That means I am writing the potential difference magnitude, or else you can take along the, okay, we'll apply the formula only. Okay, so then if I am moving along the field downward, then this will be minus final and this will be my initial, then VL minus VH is equal to minus E into dl into cos 0. Okay, because I am moving along the field direction. As I am moving along the field direction, this will be final, this will be initial. So then if I multiply the minus, then VH minus VL is equal to E into dl, then potential difference across the ends, which is magnitude, is equal to VB into dl. So this is the potential difference created, or EMF created across the rod. And in this case I can use the terms potential difference and EMF, but there is a difference between the EMF and potential difference that we see in later videos. Okay, so like this we can identify the potential difference or EMF created across the rod when it is moving in the magnetic field. But this is the particular case. Why? Because velocity and magnetic field is perpendicular to each other, and velocity is perpendicular to rod length also. Velocity is perpendicular to rod length, velocity is perpendicular to magnetic field. Under this condition you can apply this formula. But general formula I want to go for. In general, how to write down the formula? The force due to magnetic field on the charged particle is equal to, we can write down E into V bar cross V bar. This is the force due to magnetic field on the free charge. Whereas what is the force due to electric field? E into E bar. this is the force due to electric field. I'm not taking what is that minus. If you want, you can take minus E, here also minus E. Now whenever these two are equal, something like this, F m bar is equal to minus of F e bar. If both are equal and opposite, then both will cancel out. Then net force acting on that charged particle goes to 0. That means steady state condition will be achieved. Then charges will accumulate at the ends. Then there will be some potential difference created across the rod. So then I can write down minus E times of V bar cross B bar is equal to, I can write down minus E into E bar. See, if you want to keep minus, or else if you can understand the logic, it's okay. Minus of minus will become plus. Already minus is there, minus is there. Okay. So then E bar is equal to, I can write down minus of V bar cross B bar. This is the electric field value, magnitude and direction also. You can find out from this. Now this is the electric field across the rod. Now if I want to find out the potential difference, I can write down minus E bar dot dl bar. Then delta V will become V bar cross B bar dot dl bar. This is the potential difference in terms of vector form. So this is the general formula, anywhere you can apply. Let us apply the same formula to this case. Now here V bar and B bar both are perpendicular to each other. Then delta V or V bar cross B bar vector is, magnitude is VB sin 90. VB sin 90 is the magnitude, and direction is V bar cross B bar will be upward. So this is the direction of V bar cross B bar. So direction is, I am taking as something like an okay, this is x axis and this is y. Then direction will be j. This is the V bar cross B bar. But we want to find out the potential difference, obviously, which is a scalar quantity. V bar cross B bar is VB j cap, sin 90 I am taking as 1, and dl vector I am taking as in this direction. So dl vector we can choose anywhere, it doesn't matter. So if I am choosing in this direction, then dl vector and V bar cross B bar vector both are in the same direction. So I can write down dot dl bar or dl j cap. So then j cap dot j cap will be 1, VB into dl will be the delta. This is the potential difference which we got earlier. So like this you can apply this formula anywhere. Now we see the second case, that is, or second case or some other principle. Suppose this is the magnetic field. If this is the magnetic field, then I can write down, I am taking a very small part of the conductor, dl. dl is the length of the conductor. Now it is moving with velocity at some angle theta with the rod. This is the angle. Angle theta with the rod, it is moving. Magnetic field is B, uniform magnetic field is there. So then what is the potential difference across the rod? I am calculating the magnitude first. Then I can apply the formula now. I can write down two things here. This is V cos theta, one component. Other component is V sin theta. And I am taking the dl vector also in the same direction. Upward I am taking. Then delta V I can write down is equal to V bar. V bar is nothing but V sin theta I cap plus V cos theta j cap. V sin theta I cap along the x-axis. V cos theta j cap. Okay, this is V bar. Cross V bar. V k cap inside. Minus k cap. Okay, dot product with dl j cap. dl I am taking in upward direction. So my directions are x, y. Outer the board will be z. Inside the board will be minus z. So then this is, if I am taking the first one, V sin theta minus of V, I am multiplying these two. I cross k. It's I cross k. K cross I will be z. I cross k will be minus z. So ultimately this is plus z. Okay, plus V cos theta into B or BV cos theta, J cross K will be I, minus of this minus I cap. Okay. dot dl j cap. Now j cap dot j cap will be 1, then bv sin theta into dl minus of I cap dot j cap will be 0. That means what I am writing is bv sin theta into dl under ultimately. So if you see the result, you can understand one thing, that is V cos theta is not developing any in the result, final result V cos theta is not there. That means V cos theta not developing any potential difference across the rod. What component is developing? Only V sin theta is developing. That means here we can understand one thing, that is suppose a rod is there and this is the magnetic field, it is moving in the magnetic field. So again rod and magnetic field both are perpendicular to each other. If it is moving with velocity, only perpendicular velocity will make the will give the potential difference across the rod. That implies delta V is equal to, we can write down B into V perpendicular into dl. So you have to see the perpendicular velocity to the rod. So that is one idea we can understand from this. Now we see one more case, that is if magnetic field is like this. If magnetic field is in this direction, now magnetic field is not into the board, magnetic field is on the board towards right. Now I am taking the one rod which is moving with velocity v on the board. Again length of the small part is dl. Length of the rod is dl and moving in the direction of magnetic field. So that means V bar and B bar both are parallel to each other. Then what is the potential difference across the rod ends? Then potential difference is equal to what we can write down, V bar cross B bar dot dl. So this is the formula you can apply anywhere. This is general formula. So then V bar and B bar both are parallel to each other. Then this goes to 0. So that delta V goes to 0. That means no EMF is developed. So whenever rod is moving in the direction of the magnetic field, you don't find any EMF across the rod. So that is one general principle in motional EMF. Try to remember this idea. So next case I am taking, if this is the magnetic field, okay, this is the magnetic field which is into the board. Now I am taking the magnetic field into the board. I am taking the randomly one conductor. This is the now conductor. Now conductor is not straight, conductor is curved conductor. So whereas whatever previously I have taken, DL is a straight conductor. Now if I am taking a curved conductor, but I know I want to find out the EMF induced across this conductor if conductor is moving with velocity towards right. Now conductor is properly linear motion and moving with velocity in forward direction. We know that delta V formula is V bar cross B bar dot dl bar. This is the delta V. This we know. Okay. So then this can be applied for only straight parts and straight rod. Whenever rod is straight, we can apply this. So now, but this is a curved conductor, so I cannot apply the formula directly here. Then what I have to do is, what I am doing is now I'm splitting the rod or wire, conducting wire into many number of parts. Infinitesimally is very small parts. Okay, so these are very small parts. Understood? I am cutting into infinitely small parts. Now if I take any small part of it, then every small part will become a straight one. So I can apply the formula for each and every small part. Now I am taking the first small part length is dl1 bar, second small part length dl2, that one I am writing as in terms of vector dl2 bar, something like this. So this is the conductor, suppose, okay, this is the conductor, this is the one small part dl1 bar, second small part dl2 bar, dl3 bar, like that. Okay, so I am taking all our vectors. Like that, last part vector is dl n bar. So like that, n parts I have done. Then potential difference developed in the first part is across the first part V bar cross B bar dot, I can write down dl1 bar. Similarly, the second small part. Across the second small part, the potential difference developed is V bar cross V bar dot dl2 bar. Okay, and so on. The potential difference across the nth part is V bar cross V bar dot dln bar. So like this, I got potential difference across the different parts. Now I need to find out the net potential difference across the AB bar. Entire AB bar, I want to find out the net potential difference. So I have to add all the potential difference, delta V1, delta V2 and so on, delta Vn. Okay, so delta V is equal to, if I am adding all these things, I can take one thing common, that is V bar cross V bar dot dl1 bar plus dl2 bar and so on, dln bar. Okay, so if I am taking the V bar cross V bar common every term, then dot product will be the one thing common, which will follow the distributive law. So dl1 bar plus dl2 bar and so on, dln bar. So then delta V is equal to, I can write down V bar cross V bar, okay, dot. So here a magic happens. What is the magic? dl1 bar plus dl2 bar and so on, dln bar. If I am adding all the vectors like this, the addition of all these vectors, whenever vectors are kept in such a way that tail of the vector is coincides with the head of the vector, and I have to add, then I have to draw a resultant from tail of the first vector to head of the last vector. So then this will become the resultant of all these vectors, addition of vectors. Then this entire term will shrink to simply AB bar. Okay, so that means the final term, the potential difference across the final term will give you that it doesn't matter what is the shape of the conductor, it only matters what is the initial point of the conductor and what is the final point of the conductor. So it completely independent of the shape. So I can write down it is independent of shape of conductor. It's independent of shape of conductor. It's very important to try to remember. So this formula you can apply for straight conductor. Whenever curved conductor is given, this formula you can apply. So for curved conductor, remember you have to take length vector. Length vector is nothing but initial point to final point. Draw a vector that will give you the length vector. So doesn't matter what is the shape of the conductor.